Yeah.
I don't think it's yeah, it's not super high pressure situation here.
Okay. All right. So actually, let me. Where did we leave off last time? We read the first one, right?
Yeah, I think you're at the right place. The ray marching.
Yeah, I just want to kind of remember what we did last time. Okay, yeah, this exponent here, negative distance. Yeah, right, fuck. The density, the
And I think we were just starting to mention like in scattering and stuff, so like light scattering into your path. So I think
Right.
by near where we ended, we pretty much just had transmission and out scattering, maybe.
Did we got to the second chapter?
Yeah, I believe so.
Okay.
Right. Always. Right. T1, T0. Okay. Kind of. Yeah. Density in scatter here. Okay. All right. Okay.
Oh yeah, so we got into the theory of in scattering, so like light, like single in scattering,
Yeah.
but we didn't do any of the code for how to do that. So I think we're starting with how to actually implement that.
Okay. Cool. All right, then let's do the new one. All right. The almighty ray marching order. 19 minutes. Okay, we gotta double that. It's probably like an hour. Okay, to integrate increment light along the ray due to in scattering. Break down the volume. Let the ray pass through into small volume. Combine the contribution.
So Mike is really quiet for me. I don't know about for you guys.
Yeah, I'm just kind of reading it to myself. I don't know if you guys want me to read it or you want to
No,
read
just
it.
your mic volume is really low. I don't know if you can up that.
Oh, okay.
I've got it up on my computer here too. So yeah. So to integrate light along the ray due to in scattering, we'll break down the volume that the ray passes through into small volume elements and combine the contribution of each of these small volume elements into the overall object. A little bit like when we stack images or with a mask or alpha channel, generally representing objects' opacity onto each other in a 2D editing software such as Photoshop. That's why we spoke about the alpha compositing method in the first chapter. Each one of the small volume elements represents a sample in the Riemann sum mentioned in the first chapter, and that's basically approximating the integral of the light traveling the light that'll be received by your eye. So they're looking at backward ray marching here, and a fair amount of editorialization, I guess I could do here, but yeah, I'll just kind of read this, I guess, at this point. The algorithm works as follows. Find value for T0 and T1. Those are the near and far intersection points with the volume. The points where the camera ray enters and leaves the volume object. Then divide this segment defined by T0 minus T1 into X number of smaller segments of identical size. So we want to take a certain number of constant size steps, basically. Generally, we do that by choosing a step size, which is just a float that defines the length of that smaller segment. So they've got some example calculations there. And so basically what that's doing is it's marching along the camera ray X number of times, starting from either T0 or T1. And that's actually there's quite a bit to that, whether you start from the far intersection point or the near intersection point. And that changes how you actually composite the color there. anyway, the doesn't look like there's a 0.4. Anyway, each time we take a step, we shoot a light ray to starting from the middle of the step. That's the sample point to the light. And so it's basically we're saying along our camera ray, we have all these different points at a constant step size. Each one of these is potentially shadowed or illuminated, these kinds of things. And basically we want to determine that. So we're doing a second ray march then along the ray from that sample point to the to whatever light source is being considered right here. So if you look at figure 2 there, the going from T0 to T1, we have a certain amount of the pink volume that's present there. And so that's going to attenuate the light a certain amount based on what's coming from the light source. And that has to do with Beer's law. Basically how much forgetting what the term is. Yeah, like a density, kind of a term that basically just how much stuff is in between the light source and your sample point.
Okay, yeah, this makes sense.
So basically, yeah, then a key thing there is when you're doing the Riemann sum, if you've ever done your real basic calculus classes, you've seen the Riemann sums. You've got to multiply by the width of the columns there to approximate the integral. And so the idea here is that you multiply by the step size kind of thing to do that width part of the Riemann sum. That's the dx term. So the T0 for the ray sphere intersection test should always be 0 because the light ray starts within the sphere, and T1 is the parametric distance to the point where the light ray intersects the sphere from our sample position x. So we can use that value in Beer's law for the distance over which light is absorbed by the volumetric object. Okay, so then light passing through the volume element is attenuated as it passes through the sample as well. So we compute the transmission value for our sample using the step size for the distance traveled by the light beam through the volume in Beer's law, the Beer's law equation. Then attenuate the light amount by the transmission value. So that only works if you're talking about a completely uniform volume that has no features inside of it. It's just constant density all the way through. So if you had variable opacity in there, you'd have to do more to consider varying density. Anyway, yeah, finally, you need to combine each one of the samples to account for their respective contribution to the both the overall opacity and color of the volumetric object. If you think of this process backward, the volume element starting with T1, and that's which one? Figure 1. That's okay. Yeah, starting from T1 and going backwards. That's the way I've done it in the past. That's actually, it seems like the easiest way to do it, because the alpha compositing is it's the same as what you would use for graphics API alpha. It's the same calculations. You can use the equations from the OpenGL spec or whatever.
Can you just use Beer's law, like for each point along the first ray, and then just sum them up? Or I don't know.
Beer's law is basically the exponential decay. So it's attenuation from the volume there.
Right.
So you basically have to do that in multiple steps. So if you know it's uniform volume, then you know that can just be a distance.
Okay. Right. If it's not uniform, then you have to do the alpha thing. Okay. Yep.
Okay, so if you look through the camera array, the element directly next to T1 is occluded by all elements that are in front of it. So the sample that's just after the sample directly next to T0 is occluded by the very first sample, etc. So it's just kind of a back to front order dependence there. So they're saying ray marching can be easily understood now, taking small regular steps. Make sure, yeah. So it's not that's not necessary for ray marching to have constant size steps. In a lot of cases, especially when you're talking about signed distance field rendering, you're not dealing with constant size steps at all. That's actually informed by the SDF that you're ray marching. Anyway, yeah. So for this discussion, I think it's easier to talk about it in constant size steps. So anyway, yeah. Combining the samples in two ways. There's the backward sort of a term where you would do it in terms of an alpha. Or a forward term where you would be doing it in terms of like a transmission kind of a value. So it's like instead of yeah, it would be starting at the front and then going toward the back, and it would be it's basically just inverting the problem, kind of the idea. Anyway, so we will march along the ray from back to front, and this is the way I've done it in the past. This is simpler in some ways. So this changes the way that we combine the samples to compute the final opacity and color values. So once we start from the back of the volumetric object, we initialize our pixel color as the background color, and then we're alpha compositing multiple samples over top of that. In order to determine the color of those samples that we're alpha compositing, we have to get that incoming light value, and then we also need to know the color of the volume, and then additionally we need the density of the volume, which informs the alpha there as well. We need to compute the contribution of our first sample in the volume starting from T1, walk back to T0, and take a regular steps. So what is the contribution of that sample? We need to compute the in-scattering contribution as explained above, shooting an array in the direction of the light, and attenuate the light contribution using Beer's law to account for how much of that light is absorbed by the volumetric object. So it's, again, there's a lot of assumptions here made that it's a uniform density kind of thing. We're basically just, yeah, we're saying that there's X amount of distance. That means there's X amount of optical density, kind of a just stuff in between those two sample points. And so our light is going to be attenuated by X amount, kind of a thing. We need to multiply that light by the sample's transparency. Sample transparency is computed using Beer's law, using step size. Okay. So we've just computed our first sample. We move on to our second sample. So if we look at the, what is that? Unlabeled next figure. We're doing these multiple times. We're multiple times we're compositing the color with that incoming light over top. So if you see Li x0, Li x1, Li x2, blah blah blah, in that next image, we're basically, if you think about it in terms of like a rasterization context, we're basically just, it's like if you just put all those polygons on top of each other, like you're just rasterizing them on top of each other, kind of idea. So right, when they do it in terms of a transmission value, that's, like I say, that's kind of, you can do it backwards in terms of an alpha value, or forwards in terms of a transmission value. So it's kind of a, there's two different ways to approach this problem. Seems like they're kind of in between.
It doesn't look like he's actually calculating Beer's law for every step, because it's always the same x of minus step size times sigma a, right? So that's a constant.
Oh,
Yeah, I think
okay.
Yeah.
I think what's happening there is like, yeah, it's like, yeah, you're basically getting the alpha value times some distance, so it's kind of it's doing like an approximation of Beer's law there.
So basically, my reading comprehension failed.
Density and apply Beer's law once at the end. I'm not sure about that. I'm not actually sure about that.
I'll probably cover it later on.
It might do, yeah. So note from the image above, we complete two values, the overall color that's stored, and then the overall transparency. So we initialize to 1 to indicate fully transparent. An interesting choice. And then attenuate the value with each one of the sample transparency values as we walk up the ray from T1 to T0. So that's towards the eye. Right. So then finally use this overall transparency value to combine the volume object over our background color. And so we can say that certain amount of the background color was transmitted. Okay. So we can multiply by that transmission value, and then add the result. That's the accumulated color through that volume. So it's just a sum there. So we would say that this result term is already pre-multiplied by the volume overall transparency. So this is confusing you, clarify in the next chapter. So don't focus too much for now. All right, so note that also both the image above and the code below, the attenuation term example is always the same. It's the exponential of the negative step size times the sigma alpha value.
I have a quick question.
Sure.
Yeah, so is the color of the actual, what do you say? I don't know, for example, if it's smoke, like, is the color of the smoke being used in the equation at all? Because it seems like the actual volumetric color isn't used.
Sigma A is a constant. So they're kind of like doing this thing where they're making some significant assumptions here. Like, yeah, they're basically saying sigma A is a constant and step size is a constant. So exponential of negative step size times sigma A is a constant. So we can just do that for each steps through the volume.
Right.
Sorry, that may not answer your question.
It does look like they're ignoring the color. I mean, it's like a gray fog only, not a
Yeah.
colored fog.
Yeah.
Yep.
Okay, thanks.
So yeah, they're talking about pre-computing that. If you know that you're dealing with uniform volumes, if you know that's going to be the same thing every time, just go ahead and use a constant there. And in fact, they're not actually even using transmission in any of the other computations. So realistically, you're looking at a situation where you just count the number of steps you take, and then your transmission value can be, you can kind of use that constant for that. Anyway, so this is a little strange. You got top-down distant light, red color. The sphere comes from the light color. See, the top half of the sphere is brighter than the bottom half. Okay. Sorry. Yeah, down below the code block here. Yeah, I'm having to do picture-in-picture for the stream video, and then also the got the chat window up and another thing here. So
You can share your screen if that would be
I'm-
easier.
I'm on my phone.
Okay, never mind. Yeah,
Sorry, this is a little bit of a mess. I gotta get a new microphone.
yeah.
Sorry, I lost track there. My
No, that's
attention went somewhere else.
okay, so we're saying this code is not accurate yet. Missing a few terms that we'll be looking at in the next chapter. For now, we just want to be understanding the principle of the ray marching here. And so that will produce a convincing image for a uniform volume with one light source kind of thing here. So let's see again what happens when we march along the ray.
Do we want what part do you want me to look at?
I think it's right under the picture below this.
Yeah. I'm just reading along below the image they have there. The figures are not consistent. I'm right above figure 4. They're not consistently labeled.
Okay. This is figure 4.
No, the next one.
Next one, sorry.
Okay, here.
So if you look at what happens to just LIX0 as we go through the loop, we can observe that it gets multiplied by the same attenuation raised to the same power. The more we march along the ray, the higher the exponent, and thus the smaller the result, since the attenuation of the sample transparency is lower than 1. When I thought about doing this in terms of transparency rather than in terms of alpha, it's strange the way that they're doing it, because they're doing it the way that I thought about doing it in the forwards implementation and the backwards implementation. So that's a little strange, because when I was doing it for Veraldo, it's literally just alpha compositing the samples. I mean, it's literally the alpha equation to put those samples on top of each other, not keeping a transmission value.
Yeah,
Just-
it does seem a little funky the way they're doing it. Seems like forward would be better anyway, because then you can have it early out if transmission gets small enough or something.
And that's big. That is definitely a big thing. If you know that you hit some maximum opacity, then you know that you don't need to march any further. Kind of thing.
I think that's what they're doing next, right?
I think so. Yeah. So okay, no difference. There's no difference with backward ray marching when it comes to computing LIX and the sample transmission value. Okay, so at each one of those points in the volume, it's the same operation. It's basically just, okay, we ray march through the volume, see how much light is attenuated on the way to the light source. Forward ray marching, the contribution of the light scattered by this a sample has to be attenuated by the overall transmission of all samples that we've been processing so far. An interesting way to think about that is that and it's the same in both backwards and forwards. The closest points have the largest potential influence over the more distant points. So if you have a very opaque well, great. I guess that's not super relevant here because we're assuming constant opacity. Anyway, has to be attenuated by the overall transmission of all samples that we've been processing so far. LIX1 is attenuated by the transmission values of X0 and X1. X2 is occluded by X0, X1, X2. So we're going through the algorithm here. Before we enter the Raymarching loop, initialize the overall transmission to 1 and the color result variable to 0. It's interesting that they initialize the transmission to 1 in both cases. I'm not. Anyway, so for each iteration in the loop, we're computing the inscattering. That's the attenuation to the light source, LIX. And then updating the transmission by multiplying it by the current sample transmission value. Okay, so that's kind of not making the assumption that we're in a constant volume. That sample transmission would be the variable opacity in the volume. For this case, I guess it's a constant. So if we multiply LIX by the overall transmission, light scattered by the sample is occluded by all samples, including the current sample that we've processed so far. Adding that to our global variable stores the volume color for the current camera ray, and we add that by multiplying LIX times the transmission value. So as that overall transmission value becomes attenuated by multiplying by that sample transmission in the range 0 to 1, that becomes smaller and smaller and smaller and smaller. And so that contribution becomes smaller and smaller. So I've got it in code here. Again, noting that it's not accurate yet, missing a few terms we'll be looking at in the next chapter. So we want to understand the principle. So they're showing that the backwards and forwards should give the same result. So why is the forward better than backward? So we can stop as soon as the transparency gets very close to 0. So we know that transmission has gone to a very low value, so that sorry, if you scroll up just a little bit, the right above the picture with the where they're talking about here, the step 1 and step 2, just up a little bit here.
I think it means scroll down, but
Sorry, okay.
Yeah.
Well,
no, go down in the page.
no, that was the one.
Was it?
Yeah. So you see when the transmission value becomes very small, that multiplies LIX, that result is not going to be significantly changed. So if you say transmission reaches some lower threshold, we're not really going to get any significant contribution, and we can say, early out, say we're not going to take any more steps through the volume. So we go back down to choosing the step size here. So that's one of the things. If you've got a lot of stuff going on in the volume, capturing the small details can be an issue because your constant size step may not catch every single feature that's in there. You may be overstepping some solid object casting a shadow. You may be completely ignoring that shadow, and that'll create some visual artifacts there, like with the gun number 6 there. They say that's an extreme example, but that's really not that unreasonable when you think about if you've had small solid objects that are casting shadows. If you know that your volume is made out of voxels, if you want to make the assumption that they're little cubes, you can do like DDA, like there are ways to basically touch all voxels along array kind of a thing and get distance between intersection points and do the same math with not exactly a constant step size. But if you have like polygonal geometry in that volume, that's going to make things more complicated. Anyway,
So I don't understand the figure 5 where he says if your step size is too small, you're going to miss detail.
Yeah, we're back and forth on that assumption that it's a uniform volume. So this is in the case that it's not a uniform volume. We have features in the volume that are not. It's not just a constant opacity value. So if that opacity varies through the volume, we need to make sure that we get all the relevant features. Otherwise, it's not going to be representative. We're not going to get the correct color value out.
Shouldn't a smaller step size give you more accuracy?
Right. That
But
would be.
he said the opposite in the 5.
Oh yeah, they did say that. Yeah. So it would be if your step size is too large, basically.
Oh yeah, too large.
Yeah, I think some of these Scratch Pixel articles have a few typos in them, so just be mindful of that.
Yeah, we might try and get some stuff together, and I think I'm in the Discord for this. I'll try and get a hold of them. Anyway, so the reason we're array marching to take steps from T0 to T1 is to estimate the integral. As explained in the chapter before, the larger the rectangles, the less accurate the approximation. So you're basically, we're talking about step size there. The larger the rectangles, the larger the step size. Or the other way around, smaller the rectangle, smaller step size, more accurate the estimation, but that takes longer to calculate. So for now, rendering our volumetric sphere is pretty fast, but as we progress through the lesson, we'll see that eventually gets slower. This is why we're choosing the step size as a trade-off between speed and accuracy. For now, we also assume that it's uniform. See that to render the volume density as clouds or smoke, density varies through space. They're made of features of variable frequency. The step size is too large. It may fail to capture some of the smaller features. It's a filtering issue and an important but complex topic on its own. And I think that's an accurate summation. Problem might arise that requires tweaking of the step size is the shadows, like you can see in figure 6 there. You want to make sure that you're not overstepping completely the volume that's in shadow, because you want to be able to, you want to get a sample there that that contributes to that camera ray. You want to get one that is in that shadow, so that you have you're accumulating something that represents what's actually, you want some accurate representation of an interval. So small solid objects are casting shadows in the volumetric object. You will miss them if your step size is too large. So that doesn't tell us how to choose a good step size. In theory, there's no rule. So essentially have an idea of the size of your volumetric object, or the size of the texels in your volumetric object if you're putting a 3D texture on it. Note also that that's variable, because if you're looking at some arbitrary direction through there, the distance you travel through any given voxel is not going to be the same. Because you're not necessarily going the same path through each one of them. Anyway, so saying, yeah, basically just pick some constant here. So choosing the step size empirically by considering how big the objects are in the scene, it must be some more. Indeed, a pixel that is a discrete object can't represent details from the scene that are smaller than its size. We won't get into much more detail here because filtering is worth less on. Okay. Something relevant here is, if you've got a, actually, yeah, it's just going to be confusing. So looking at, what are we doing? Projected pixel width is 2 times the tangent of pi over 180 times the f of v times the image width, 2 times the image width over. So basically just trying to come up with some way to estimate that step size. There's a lot of different ways you can do that. It could just be a small constant, or you solve for T0 and T1 and you've got a distance, then you've got some maximum number of steps. You establish some maximum number of steps, and then you clamp that to some minimum value, and then you can do it that way. If you divide the total distance by the number of steps, you clamp that to a minimum value. Anyway, so writing production code would require storing the ray opacity and color with the ray data. We can ray trace the solid objects first. Not actually sure what they're trying to say here. Storing ray opacity and color with the ray data. So I guess we're talking about, like, if you have multiple of these volumetric objects, then we need to composite through all of them, basically. Volumetric object can be made of a collection of combined objects such as cubes or spheres. In this case, we may want to combine them in some sort of aggregate structure. Remarching, blah, blah. Yeah. There's a lot of different ways you can approach that. If you have multiple features that you're remarching through. So next, in the third chapter, we're adding a more physically accurate type of model here, looking at being able to read and understand other renderer code. Yeah. So I think this is a good, there's some inconsistency with the first half, but I think that, there's a couple things I actually have some notes on, but yeah, I think this covers a lot of the material there. Do we want to do the next chapter?
Yeah.
Where's the source code? They said this is the source code for this MD.
It should be somewhere. I think if you scroll up to go back to that tab, where the source code was. Go to the bottom one. That might.
This one? Yeah.
Yeah, I
Right?
think they have the code and the markdown documents in like separate folders.
Oh yeah. chapter 2, 3, 4. So chapter 2 is probably the one we just went over.
Yeah. Oh, there it is.
I think that's right. Yeah.
So it's this one. Yeah, okay. Bookmark this. I'll keep it open. Okay. Do we want to go to the next one? Next? Whatever.
Yeah, okay.
I'm up for it. It seems more complicated and interesting, but
Yeah.
We're on chapter 3. This is ray marching, getting it right. Okay. So this will be a little bit longer one. I'll just go ahead and say as a little bit of a forward here, the full scattering that happens with all the rays is too complicated to compute for real-time stuff. So there's a lot of approximations for this type of stuff. We can't be considering bounces and bounces and bounces through volumes for real-time stuff. So we accounted for only 2 types of interactions making up this medium. That's absorption, that's the attenuation along the camera ray, and then the in-scattering, which is the attenuation on the way to the light source. To get an accurate result, we need to consider more than that. So we divide them into 2 categories. Interactions that attenuate the energy of light beams as they pass through the medium to the eye, and those which contribute to the increasing of the energy. So it's a sort of additive and subtractive kind of a thing. So absorption is the amount that's absorbed by the volume. That's your Beer's law. That's some amount of attenuation through the volume. And then you've got the outscattering, which is that's kind of more complicated. That's the actual physical behavior of the light. It's got some probability of scattering outwards, just kind of in some random direction. Some light is traveling towards you, the viewer, but I decided to scatter some of it in random directions so you get less. That's what they sum it up as. I think that's pretty good. So then there's ways that they could gain energy, and that's through emission. That's if your volume emits some amount of light, it's like, for example, a flame, or through in-scattering, and that's along the lines of what we did with the talking about attenuation on the way to the light source. I gathered X amount of light that's coming to me from all directions and spit some of it in your direction. To get some light that wasn't initial. Anyway, yeah, so in our computation for how much light we lose as light travels through the medium to the eye, we have to account for both absorption and outscattering. But out and in scattering are caused by the same type of light particle interaction, which we've been calling sigma S. So sigma S is also responsible for how much light we lose as light travels through the medium to the eye. We need to account for it in our Beer's law equation alongside the absorption coefficient sigma A. So that's the amount that's absorbed due to the opacity of the light. So this equation is used to both to compute LIX and the sample transmission value. So it's relevant for both the camera ray and also for the ray on the way to the light source. And so code then becomes changes in red, and nothing is highlighted red for me. So anyway,
It's on the last line. It has the HTML like bracket there, but didn't show.
so
Yeah.
okay.
Right.
So we're talking about the extinction coefficient. So that's basically the sum of your absorption and your transmit. Sigma T. Okay. Sigma T is the extinction coefficient. So we've got sigma A is the absorption coefficient. We've got sigma S is the scattering coefficient, and then we've got sigma T is the we've got some typos here. Sigma T equals sigma A plus sigma T. I think it's probably sigma T equals sigma A plus sigma S.
Yeah, it should be sigma F.
Okay, yeah, I need to take some notes. Anyway, so we've got those different coefficients, and then you need to multiply by the. I'm not seeing the changes in red on my thing. That's
It's markup. It's HTML markup. It's just spam.
oh, okay, gotcha. All right, yeah. That's good. Okay. The density term, consider the scattering and absorption coefficient, control how opaque the volume is as uniform across the volume itself. So any point inside that volume, we know that it's a certain opacity. We know that there's no variation in opacity through the whole volume. That's kind of the assumption that's been made so far. That's not generally true. If you think about you're looking up in the sky, you see clouds, you see, whatever these types of things are. There are variations in opacity in the volume itself. So it's often referred to as homogeneous participating media. This is generally not the case with volumes in the real world. Clouds or smoke plumes are heterogeneous participating media. So we only see how to simulate volumetric objects with varying densities in the next chapter. But for now, let's say we want to have some kind of variables that will scale our scattering and absorption coefficient globally. Let's call this variable density. Okay, so we're wanting to just globally adjust that volume opacity. Right? So we're saying that, density is just a term that's been added in there. Okay. Keep in mind that sigma S is used 2 places in the code. We're looking at spatially varying density in the next chapter. Now something is interesting here. When the density is 0, nothing is added to the result variable. So in other words, where there's no volume, 0 density, there shouldn't be any accumulated light because there's no scattering that happens. The in-scattering is not going to happen the way that you would expect when we're looking at the remarching like we discussed in the last chapter. So yeah, if result wasn't 0, then there's no volume. If result was 0, then there's no volume.
Typo.
Yeah, this needs a revision pass here. That's why in the previous chapter we mentioned that the result was already pre-multiplied, that is multiplied by its own opacity. It's greater than 0 where the density is greater than 0, or 0 if that density is in fact 0. I guess we've got I'm missing omega image. Not quite sure what that means. In-scattering contribution should be computed with the following equation. So Li is the in-scattering contribution. X is the sample position, and omega is the view direction. Okay, so normally omega is always pointing in the direction of the radiance flow that is from the object to the eye. So it's the direction the light is actually traveling. Since omega prime denotes the light direction, that's the opposite direction, I guess. The Lx omega prime is nothing more than Lx in the code that we saw before. That's the amount of light that's received from the light source as it's attenuated through the volume. Light contribution or incident radiance, which we've been calculating the value of in our code so far. So it accounts for the amount of light that's coming from a particular light direction. Omega prime at sample point X after it has traveled a certain distance through the volume. But since we haven't introduced the term right after the integral sign, that's called the phase function. This is, yeah. I know Jaker's dealt with a little bit of this. This can get complicated in a hurry. That's basically, you're looking at the relative direction of your eye ray and then the distance to the light function, to the light source.
I think that's Victor. If you scroll down a little bit.
Yeah, the isotropic and anisotropic. So it's kind of looking at a situation where, based on properties of the material, it might have more forward scattering or back scattering kind of behavior, and it's got a significant impact on the way that things look, but it's a little bit complicated to kind of get into. We'll see how they introduce it here. So put into words what the equation says. The integral means that the in-scattering contribution can be computed by taking into account the light coming from all directions over the entire sphere of directions. Okay, so I guess the earlier code is making the assumption that it's coming from a single light source. Here now we're saying that we're taking the integral over the entire sphere around the of directions. So to compute the appearance of solid objects, we use functions called BRDFs that gather light over the hemisphere of directions instead. Solid objects, we don't care about light coming from under the surface, except for translucent materials. That's another long story. Interest in this topic, these other links, back to phase functions. So isotropic means that we're equally scattered in all directions, and anisotropic means that there's some bias in some direction. So it's not uniformly distributed over the sphere. So when a photon interacts with the particle, it can be scattered out in any direction within the sphere, possible directions around the particle, where every direction is equally likely to be chosen in any others. In this case, where it's equally likely, we speak of an isotropic scattering volume. Iso as in like same, and then I think tropic kind of has to do with like directionality. Anyway, so that's an isotropic volume when it's equally likely to go in any direction. Isotropic scattering is not the norm. A lot of volumes tend to scatter lights in a restricted range of directions. And speak of an anisotropic scattering medium or volume. Phase function is simply a mathematical equation which tells you how much light is being scattered for a particular combination of directions. The view direction omega and the incoming light direction omega prime. Function returns the value in the range 0 to 1. So this is an additional attenuation factor that kind of basically like, in addition to how much attenuation happens from marching through the volume, you have this other factor now that is scaling like, it's just another scale factor that has to do with the directions in play. Basically, like if you're talking about the direction to the light source and the direction to your eye, then that's gonna be the direction in which you're sampling the that phase function. The way they're talking about it here, I guess, kind of seems like that's something that would be evaluated once per sample through the volume, but I've seen an optimization where it's calculated once just for the camera ray and just kind of go from there. Because it's kind of one of those close enough kind of things. So consider the directions from which light can come around the particle. How much light is being scattered out around the same particle can't be greater than the sum of all incoming light. It's the reason why the phase function needs to be normalized. We need to say that the phase function, when you integrate over a sphere, needs to be equal to 1. And that's basically just so you don't have any, like, energy is not created or destroyed kind of thing there. So it's not going to create light that wasn't. And the idea is basically just not creating light that wouldn't be incident kind of thing. So if the function was not normalized, it would either end or. So you swap omega and omega prime, the result should be the same. And that's it's the same with a lot of BRDF type functions. Okay, so figure 2 shows kind of what that angle is that we're using to look at the phase function. And I think a lot of times that phase function is just a one-dimensional function that's just giving the angle. You give the function the angle, and then it gives me back the attenuation factor. Phase function is just kind of like a BRDF. It's the same idea. So only needs to depend on the angle between the view and the incoming light direction. So this is why it's generally defined in terms of theta and not those two vectors. Just the angle between the two vectors. So we take the dot product, we get the direction, we get the angle, then we take the cosine and solve for the angle. So what do these phase functions look like? Simplest one is isotropic volumes, because light coming from all sets of directions within the sphere, that direction is equally scattered in all sets of directions of the sphere. Integral over the spherical domain needs to be normalized to 1 over 4 pi. So that's constant, doesn't take the theta value into consideration. Theta, not used, okay. It's expected since the direction of the outscattered photon is independent of the incoming light direction, and all outscattered light directions are equally likely to be chosen, which is why the equation is constant. It's not very hard to understand this equation. So this is not very realistic. I don't actually know any materials that are isotropic volumes, but the idea is basically here that you look at it in any direction, it's going to act the same. No effect based on where the light source is. In reality, if you look at like clouds or things like that, it's going to be very different based on whether the sun is kind of in front of you, if that's an acute angle between your view ray and your light ray, or if that's kind of like an obtuse ray. So it's more than 90 degrees, then you're looking at like what's called backscatter. And so they've got different ways to kind of look at that. So area of a sphere is 4 pi steradians, and that's basically the surface covered by all our incoming directions. If you think of this direction in terms of differential solid angles, and thus the phase function ought to be 1 over 4 pi to satisfy blah blah. Okay, so the Henyey-Greenstein function is basically just creating this lobe that it's, if we look at the circular, or I guess what I call it, polar plot here, that's like the red ovals here are looking at I've seen it called the eccentricity value there, or asymmetry factor they call it here. That's basically looking at how to bias that towards on the right we're biasing it towards forward scattering, and on the left we're biasing it towards back scattering, and that has to do with the fact that, or is that backwards? In any event, so it's you set that factor to, and a lot of times you'll be combining a couple of these. There's a paper that I'll find later. It's the movie Oz. They had an approximation where they basically just had this same function with the Henyey-Greenstein phase function, but they did kind of a multiple octaves kind of thing where they did like they combined multiple of these lobe functions to create the final phase function. Oh yeah, I won't be able to find that quick. I don't think. Or maybe it will. No, it won't. Just kidding. All right. It was a little bit more complex indeed. So as you can, you can imagine, it has another value called G, which is the asymmetry factor, and that's in the range -1 to 1. Parameter lets you control whether light is scattered in the forward or backward direction. So it's greater than 0, it's out scattered. That's mostly forward scattering. When G is less than 0, it's backward scattering. So I guess I was right the first time. It's forward scattering on the right and backward scattering on the left. That has to do with the angle. If you look at the polar plot there, it's 0 degrees on the right, or radians, I guess, and pi over 2 at the top, and then pi at the on the left there. So it's a little bit more complex. This, yeah. So figure 3 shows what the function looks like for different values of G. So we're going through and looking at a proof. Don't need to integrate the function over the sphere of directions because our directions say that dw are defined as terms of solid angle. Right, differential solid angles in terms of Yeah, I might have to take your word on that one. I like the way that they ended that proof with the XX, finish this bit XX. Anyway, other phase functions exist, such as the Schlick, Raleigh, or Lorenz-Mee scattering phase functions. They've been designed to fit the behavior of different types of particles. In practice, it's better to use the Raleigh function when you attempt to render volumes that are made of tiny particles. And the Mee function is better for larger particles. And that has to do with the physical properties of the particles in like the atmosphere kind of idea. The Hennier-Greenstein function is often used in production rendering, kind of rendering we do in movies because it's quick to compute. It's just, 1 over, whatever it is. It's just, it's a pretty simple calculation. So, so looking at doing that calculation to get that attenuation from the phase function. Then we're looking at different biases here for the different phase functions, how that kind of varies in terms of backscattering and forward scattering. Sequence of Jaker can speak to this as well. There are tools out there that will give you a lookup table that you basically, for any given direction, for any angle, instead of just doing these approximations with the analytic function there, you can get a lookup table that gives you all the physical features of what that phase function would actually be doing.
Yeah, if you use Hennier-Greenstein or Schlick approximation, you won't get like the fog bow from looking away from the sun. Or there's also another effect that you miss called glory, which is when you're looking directly away from the sun. There's like a small bright spot. So you'll miss those effects if you use the approximations.
Those are those are major contributing factors to what makes like a sunset or whatever look like it does, kind of thing.
Yeah, later on I can show that in my application if people are interested.
Cool. Yeah. So we're looking at the Hennier-Greenstein function is simple, but can offer a good fit for real world data. Can use a 2-lobe by combining 2 of these. For example, a positive G value and a negative G value. And LARPing between these 2 phase function results. And because the I should say it. The idea is you want to keep that integral of the phase function at 1, so that's important. So for clouds and haze, use a high value around 0.8. I've got some different ways you look at that. So jittering the sample positions. This is actually this is very relevant. It's like we always positioned our samples in the middle of the segments. We took a constant step size at every sample through the volume. There's a known constant distance between the samples. One of the major issues that can create is a banding issue, where we have those constant steps basically it's creating a quantization error where, like, okay, we have n number of steps, then we went over to this slightly narrower slice of the volume, then we had like n-1 steps, blah blah blah. It's just kind of this idea of just it's creating this uniformity that it creates a banding in the output. So when you jitter the sample position here now in terms of like plus or minus the step size, we want to say that it's somewhere inside of that step rather than necessarily right at the center of that step. That can help break that up. That can adds a little bit of noise to help with the quantization error that happens there. It's essentially just it's a lot like dithering. That's basically what's happening there. So yeah, if you're seeing figure 4 there, that's looking at how we'd be offsetting that sample point within each one of those steps, kind of thing. Where rand is a function that returns a uniformly distributed number in the range 0 to 1. Okay. So we call this stochastic sampling. Can't say that it's better because we now replace the banding with noise problem on its own. And that's same issue with dithering. But anyway, result is still visually more pleasing than having those discrete bands because those don't really look realistic at all. To reduce the noise, using more elaborate ways of generating sequences of random numbers. However, this version of the lesson, we will skip this, and there are books written on that topic. Okay. So when we break from the Ray-marching loop, when we reach the that transmission value at some lower threshold, we are if you say this, you break out of the loop when you're lower than 10 to the negative 3, you might consider that computing the samples for the remaining half is not necessary. And in a lot of cases, if 1e minus 3, you're looking at 0.1%. So that's kind of, how much contribution are you actually going to get in the output? Is that actually a quantifiable amount? Maybe, maybe not. So you just got to pick your threshold there. You can do so by breaking out as soon as you detect the transparency is lower than that minimum threshold. Considering that Ray-marching is rather slow, we want to use this optimization as much as possible and not continue to Ray-march in areas of the volume where where there's not going to be any contribution to the output. We'll save a lot of time when there are very dense objects. In particular, if you think of a very dense volume, you've got 100 steps that are being taken through that volume, but you reach a transmission value at that lower threshold within like 3 steps, then you really don't need to take any more steps. You can just say, all right, that's the final color. So figure 5, looking at basically, they're calling it Russian roulette, but I'm not sure that that's accurate. I think that refers to something else. Stop Ray-marching when pass their transparency test and do nothing else. This would be statistically wrong. So somehow introduce some bias into your rendered image. Look at figure XX. Oh yeah, this is not ready for publishing. So as you can see, the red lines indicate the threshold below which we stop Ray-marching. If we do so, we sort of remove the contribution of the volume that's below and beyond the curve along the x-axis. And sure, some amount of it is negligible. That long tail kind of thing is, depending on your situation, you can consider that negligible or not. However, if you are a thermonuclear engineer trying to simulate how neutrons move through a plate, that's not acceptable. You need higher precision. I don't know if we need to satisfy thermonuclear engineers' expectations, but so method we'll be using is called Russian roulette. That's another thing that comes up a lot in Monte Carlo methods. So it's kind of it's like a randomized early out that has a compensation factor. We pick a random number in the range 0 to 1 and test whether this is greater than 1 over d, where d is some positive real number, greater than 1. We have we've got this probability in the range 0 to 1. If this is the case, we break out of the loop. Otherwise, we continue. However, we multiply the current transparency value by d. Value d here represents the likelihood that we will pass the test. For example, if d equals 5, the chances of the ray marching loop being terminated would be 4 out of 5. This makes hopefully sense. If the random number is lower than 1 over d, you say kill the photon. It's gone. You can't do anything with it anymore, right? So we know that that's reached the extent of we know that that's reached the maximum extent of the contribution that it can give. Or we decided that with this Russian roulette method here. So they've got some code here that shows kind of how it works. There's if you look at ray tracing stuff, you'll find better explanations of how this actually. The first 3 chapters of this lesson cover what's needed to start rendering volumes to a point where if you're confronted with reading other people's code, you should now be able to make sense of what I think once you understand what the phase function is doing, I think you pretty much can figure it out. It's okay, and then they're looking at PBRT to look at their implementation of volume rendering. Okay. Don't worry if you still find it overwhelming. It's serious to get familiar with all these concepts. Yeah. And then so we've got some source code. Yeah. So we're talking about some different exercises you could do if you're interested in looking at some of this yourself. How can you test that the Russian roulette method works? Can you validate that against some reference? Can you take some massive number of steps and say that that's equivalent? Can you prove that to yourself, kind of thing? Can you make the code work for an arbitrary number of lights? Instead of just LIX being the attenuation to a certain light, maybe it's multiple lights. Maybe there's light coming from multiple sources. Move the camera around using matrices. That's just how you would generate your view ray. Make it work with the camera inside the volume. So you would be taking that. Yeah, that's just your near point then just becomes the minimum of the distance traveled to the near intersection point, or just the camera itself, just at 0. Sorry, I'm at the bottom where we're looking at exercises. Then another thing I mentioned is replacing the sphere with a cube, adding a timer to measure the amount of time it takes. Blah, blah, blah. Okay. So congratulations, you made it that far. Graduated. GraduPixel is delivering you a virtual certificate with honors. Congratulations, everybody. The core of how these algorithm works has been covered. Remaining chapters are about using what we've learned and having some fun and making cool images. Finally, in the last chapter, we'll be taking everything we've learned and seeing how it translates into the actual equations used to describe the flux of light energy as it travels through and interacts with participating media. Cool. Probably call it there.
Man, that was a long one. Very long too.
Yeah. Cool. Does anybody have any thoughts or questions before we do anything else? Or
So do we want to continue this and read some of the other chapters?
Hell no.
I think
I think-
Okay.
a
Sorry.
little late for tonight.
I mean, not today. I mean, at future meetings.
Oh yeah.
Yeah.
Definitely.
Yeah.
I kind of want to try this out. It seems not too difficult, but
I've had more of this in my life than I have ever wanted.
okay, fair enough.
Do you want to look at Graphic Programming Weekly?
Sure. Cool.
I can share if you want, or
Yeah, go for it.
I'm not able to right now, but yeah.
yeah. Share. Oh, let me make this nice and big.
I think this is last week's, right?
The 19th was last week. Yeah, I think.
What's that?
Didn't get one this week.
I think there is a new one. I got an email this morning.
Yeah, me too. I deleted it though, so
I thought I saw the thing on Twitter. And
Wait, did we? Oh, this is
Uh,
old, right?
Yeah.
go to issue 280. Like, yeah, just manually type it in.
Interesting. I clicked on the top one, but I guess I didn't look at the date.
it didn't get added to the index page, I guess.
Ooh. I mean, I already knew about this, but take a look at this. Fidelity Effects SDK. Oh, let me zoom in on this.
What else is in the that SDK?
A bunch of stuff. So it's like, actually, it'd be easier if I just have all this stuff. It's got FSR 1 and 2. It's got like a single pass down sampler. I don't know about the sorting and the blur, but I guess that's those. It has shadow and reflection denoisers and a bunch of post-processing stuff.
That's cool, actually.
Right.
That's more than I thought.
Yeah, it's pretty neat. Funny is calling the last one not easy to integrate. The whole PDF. That's probably just it's all the different components. Yeah, you can only get the DX11 backend by request if you're a privileged partner.
Interesting. I wonder why.
I want to focus on explicit APIs, I guess. Yeah, this is pretty long, so it shows how to install and run the samples. Yeah, okay, I think you get the gist.
Just before we move on, has anyone looked at any other GDC stuff or like paid for it? I guess.
Well, this is actually a GDC thing.
Yeah, so I'm just curious if anyone has oh, like this distance field one is too.
Yeah, this one is interesting. The a
Oh, so-
voxelizer, sort of.
Real sparse distance fields. Cool.
Yeah, I'm like halfway through the YouTube video myself. Basically, you give it your scene, and it spits out like a sparse distance field, which you can use for various effects. Here's a visualization of it, and you can see it has like levels of detail with distance. And the algorithm's kind of complex. Optimizations. Oh, and here's a level of detail.
Do you know if this is substantially different from, like, I know in Lumen they were doing a SDF like representation of the scene as well. So do you know if they're doing anything like this?
Oh, this is an SDF representation of the scene.
I just mean like this technique of like having the sparse and better representation of it, I guess.
Stuff like this is really important.
Sorry?
Stuff like this is really important for if you want to train Raymarch meshes, things like that. Because trying to iterate through all the triangles and doing a signed distance field for every triangle is like basically a non-starter. You don't want to be doing all that because there's many triangles. So
here's some use cases for it. And that's very cool.
Cool. There's another article I found. Let me try and find it again real quick. It's kind of dealing with some similar stuff.
I remember the Claybook engine was using something sparse distance fields or something.
Yeah, I think it's kind of like that.
I've also heard it referred to truncated signed distance field as well.
Is which?
Oh, I get it, because it truncates after a certain distance.
Right.
Okay, second spherical Gaussian or Gaussian blog I've seen.
Seems like you could you do some if you're really going to do phase function stuff, and it's kind of related.
Hey, didn't we look at the spherical harmonics one last week?
Yeah, we did.
Yeah.
Maybe, yeah.
So I think the phase function had the extra constraints, so it's a little bit simpler than spherical harmonics, right? like the angle, like dependence or whatever it was.
I think it's pretty similar because it basically takes one parameter, which is the angle,
Okay.
and it spits out some value.
But it probably, I mean, spherical harmonics are more general than,
Right.
yeah.
I think the problem with spherical Gaussians is that actually computing, or not computing, but creating the representation requires like a fancy math solver, whereas spherical harmonics is basically like plug in your numbers into the basis equations. Orthogonality and rotational invariance.
Orthogonal. So rotational invariance is probably just the fact that you could offset those by some angle, but rotational invariance, I'm not really sure what that's referring to. Or the orthogonality, I guess.
Oh man. A purple heart shape. Nice.
Cool.
Yeah, so I guess if you're ever looking into baked lighting representations, spherical Gaussian is or something you could take a look at.
Sounded like only really for specular though.
Yeah. Deep neural networks. Okay, I'll give it a shot. Second part of a mini series.
I find coming at neural networks it's very complicated unless you go down to like the most trivial neural network that you can think of, kind of thing. Like I found a YouTube series that I'll probably never be able to find it again, but they were just doing it in terms of like it was like a handful of numbers and like just kind of what the relationships were through the different layers and like how it did the summation and stuff like that. But I think that can be helpful to help get a picture of what the hell these things are doing, because I think when a lot of these things are presented at a very high level and kind of don't really have context for it.
Yeah.
I think convolutional neural networks aren't too bad, but I find that they're always described with the exact same diagram, and I find that diagram very confusing looking.
Which one? This one?
No,
Or
let me find it.
at least convolution is something that I understand. Yes.
Well, convolutional neural networks just does convolution, except that it's higher dimensions. It's not just like 2-dimensional.
That's true.
I mean, it can be 2-dimensional, but usually it's higher.
I feel like this is what you always see to describe a convolution, and I don't know. I've never found this intuitive, but yeah, it really is just like if you think of it as just doing a convolution, it makes a lot more sense.
Yeah. I don't know what the heck the max pooling layer 1 is, but
Max pooling is just like kind of like taking the maximum in a region, and so like a square region, and then like outputting one number for each square region, each tile, I guess.
Okay, so it's sort of like a max reduction.
Yeah, it's a max reduction. Yeah, exactly.
Cool.
So yeah, the word pooling is throws you off, but it's just reduction.
Kind of long. So convolution. Convolution basically a filter if we were to simplify it way too much, and a tensor is basically a matrix if we simplify it way too much.
Yeah, it is.
I think that pretty much covers it. Yes.
Yeah, but when you have dilated convolutions, it actually acts a little bit differently. But for regular convolutions, it's pretty much the same.
I mean, regarding like the diagram that Owen shared, basically those layers as as you start, they're basically trying to capture like the very primitive features of your image, for example. So the very early things will be learning how to understand lines, for example, or lines at an angle, and so on. And then as you move forward with these max pooling operations, you're actually starting to look at higher levels of these features. So, okay, now I have lines, and if they are at certain angles, then I'm seeing boxes, for example. And then as you move down the layers to the right, you're starting to understand what is a face shape, because you now have what all the knowledge about all the lines, and a face is a circular thing, for example. So you just accumulate different features as you go, but as you move forward, you're starting to look at it from a much more abstract view or higher level view. You're actually looking at objects and not the individual features. That's like the basic intuition behind this.
Oh, okay. So each layer adds like more complexity, basically.
Looking at
Yeah.
higher feature stuff.
You end up training each layer separately,
Okay.
or you just train the whole thing at once?
No, you train the whole thing at once. It's end to end. So the back propagation goes through all the layers.
But you could freeze some of the layers. I guess I'm making it more complicated than it has to be. That, but yeah, there are options to train just parts of the layers for fine tuning, for example.
But
Ah,
it's,
yeah,
I
yeah.
guess it becomes really like important which kernels you pick, right? If you're trying to select lines or angles.
No. I mean, that's the point of the neural networks, is that you don't handcraft those kernels. The kernels themselves will be trained. Those will be the actual weights that you learn during the training process. That's the magic of it, at least.
But then it's like you're saying that this layer does a certain function, right? But then you don't really know that layer does that function, right? If you're just training the whole thing at once.
Yep. And
You
there's
kind of just have to look at it afterwards, right, and see like
exactly.
Yeah, it ends up being very hard to reason about a lot of these things.
I think you guys just helped me understand convolutions in an intuitive way for the first time. It's like it's a filter. A filter is like a simplifier, basically. You take a big complex image, simplify it to a lot of little pieces. You do that multiple layers or multiple times through multiple layers. And then you work backwards. And then you compose your image. It gives you a label, like cat, dog, or whatever.
Yeah, for classifiers, that's how it works. For like, if you have like auto encoders, then you end up with image to image translation. So you basically go back from this kind of like reduced form back to an image. So you kind of like have a reduction and then kind of an expansion back into the image.
I see.
So you could like, for example, like convert from an image to a depth map or something, or a image to like a mask of a face or something like that.
Then it's like generative, but it's like going the opposite way, making it more complex. Classifying is like simplifying, right?
Yeah.
Down to a label.
It's like giving one number or like a couple of numbers output from many millions of numbers.
Interesting. Pretty cool.
There's been a lot of terrain rendering stuff recently, it seems like.
I think it might have all been the same video series.
Oh, okay.
This is the guy that uses Glut. I think.
That you remember him as. Oh, note to self: never use Glut.
I met the guy who wrote Glut, Mark Gilgard.
Nice.
I've actually met him too.
Oh, all right.
He came to my work one time. I didn't realize that was something he did.
Man, so alias in this video.
Did you get into doing different LODs of different patches, and like how do you join them? Because that always seems like the hardest part is.
Yeah, I showed how to handle like cracks and stuff like right here. So he talks about when two different LODs are connected, and then you have to like eliminate certain vertices to prevent like T-junction artifacts.
Does this work for like any kind of topology, or is it just only for like square meshes?
I don't know.
I assume that the algorithm here is just for squares.
Yeah, it looks like subdivided squares, yeah.
But something I've thought about doing is, oh no, it wouldn't work, is you just add a triangle in the gap between the two LODs, but then you'd have a vertical triangle, and that wouldn't, well, because you'd have a flat surface. Yeah, so this one's much nicer.
Have you seen Brian Karras's presentation
Yeah,
about like developing nanite?
The trick is to not get really thin, long triangles. You want the kind of more, what do you call it, equilateral looking triangles.
Yeah. Healthier for the GPU.
Yeah, I thought the nanite technique was good, interesting.
What the? Who's this?
What was the presentation you mentioned, Jaker?
No, I actually don't know who this is.
It's you. I think this might be the one, JB. I think.
Hmm.
I presume everyone is familiar with the concept of a BVH, but I'll go through it kind of slowly just in case. I'll take a look at that after this one. Yeah, so this article is pretty low level. Yeah, so AMD hardware ray tracing acceleration only adds intersection tests, but the shader compiler shall also add the code for traversing the BVH. I guess it doesn't say what NVIDIA is doing yet, probably farther down. Well, also NVIDIA's, they like don't share how any of their stuff works, so
Yeah, they tend to be the
annoying. Oof.
Even all the content aside, these are very pretty pictures to look at.
I like the debug views. They look really cool.
Yeah.
Yep. And here are some performance counters in RGP. Whoop. Okay, so it's low level stuff. And comparing a different ray tracing game.
Soft.
Man, looking at these views gives me PTSD of the ray tracing titles I've had to optimize. Yes. Although it's not like you can choose, or it's not like it's easy for artists to choose what geometry doesn't go into the BVH.
I wonder if there's any way to provide that kind of info. Like not right now, but I mean in the future with more like better authoring tools.
Yeah, I could see it being sort of like a collision, a separate mesh, kind of like a collision mesh, or like a alternate level of detail.
Hmm.
Yeah, so I think in Vulkan term, this would be a ray tracing pipeline. And then second one would be ray query extension. Or actually, I don't know. No, I think that's irrelevant. I think it's something else. Right?
Do you
because
know
can
what?
have- Sorry.
Sorry, I was just gonna say, like, do you know which of these is more popular in production?
No, I don't. But yeah, it's interesting.
So the indirect thing that they're talking about, that's the all the structure of like any hit, blah 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 blah. Those types of things, or that there's different types of shader for the ray tracing. I guess I'm not really up on the low level of how this works.
I'm not sure because I don't know if Vulkan actually has a an analog to this first one. I think of it because that's one
Inline
like
rendering?
program.
Inline ray tracing is what Vulkan does, right?
Vulkan has both ray tracing pipeline libraries and where
Ray
you
query.
just ray query, where you just send off a ray query inside-ish, compute or pixel shader, and then
Oh, so did this first one be ray query then?
yeah, inline is ray query and indirect is pipelines, I believe. A
Okay,
ray tracing pipeline.
that makes sense.
That's my understanding, at least.
Okay, now we're gonna see what NVIDIA's hardware does.
I deal with most of the stuff through layers of stuff, so it's kind of I don't really get a good view of how it actually works.
NVIDIA
Sounds like the disclaimer at the top of the article says some of this may not be true, but because I think NVIDIA probably hides some of the details about their BVHs.
Yeah. So I guess take this BVH information with a grain of salt. More performance counters.
I think I'm going to hop off here in a second. Do we want to plan on just continuing with the volumetric stuff next week?
All right. Sounds good.
People are into that.
Sure.
Cool. Sounds good.
So how does NVIDIA actually accelerate ray tracing tests?
Magic.
Or ray tracing in general? So do they have...
It's on
so
the
AMD
hardware.
AMD has just the intersection test in the hardware, but does NVIDIA put the BVH traversal in the hardware as well?
Yeah, they do.
Okay.
Need to leave. So
Yeah, and then Pascal Rest in peace if you try doing ray tracing on that.
That's like the 1000 series, right?
Yeah, because all
Me,
done.
right?
Nice picture.
Oof, right above there, it said one dispatch ray call cost 26 milliseconds.
Yeah.
I mean, it's a nice picture of what I think is a kind of ugly GPU. The previous generation had a bunch nicer looking.
Yeah, so Pascal gets really bad performance, predictably. If this person really likes benchmarking stuff on GPUs.
How does one micro benchmark a GPU?
I guess we're about to find out. Well, they probably focus on like benchmarking a certain aspect and then write a shader that you know, like hammers that one thing they're trying to benchmark. A cache and memory latency benchmark. That's some information about the cache. Oh. Okay, I guess they don't say how they implemented the benchmark. Maybe if I scroll down, I'll be there. Or not. Oh, nice.
Memes.
Yeah. No wonder. But yeah, I guess benchmarking memory bandwidth and latency is not that hard. You just gotta issue a bunch of loads.
Do you not have a scroll wheel?
Well, I figured that using smooth scroll would be more more pleasant for you guys. But yeah, I have a scroll wheel.
Oh. Honestly, if you move it anything but a snail's pace, the compression just kind of eats it anyway. So
Oh,
if you
so
want to
you're
move
saying
a
it's better if I